Space and human brain. Flight into space to planets and stars has been the dream of mankind since time immemorial. With the launch of the Sputnik satellite into space in 1957, that dream came true, and the space age began. Neil Armstrong moon landing in 1969 marked an important milestone in extraterrestrial exploration. Today, we are going to talk about a trip to Mars. Technological advances have been made for longer journeys in space. However, the effects of these space trips on the human body have yet to be studied. It is generally accepted that the space age began in 1957, when the Sputnik satellite was launched into space. Yuri Gagarin became the first human in space on April 12, 1961. After that, countries such as the United States, the Soviet Union, France, the United Kingdom, China, and Japan sent manned spacecraft and artificial satellites into space many times. At the end of the last 60 years, space has now become a satellite dump. Most of these satellites are communications, surveillance, and spy satellites. Science stations such as Mir and Skylab were also built, and many scientific experiments were conducted. Then, in 1998, the International Space Station, ISS, was established, and scientific research continues today. In recent years, these studies have focused on how living things and humans can live and reproduce in space, and how they can protect themselves from the harmful effects of space. Today, mankind's greatest dream is Mars, and establish a permanent colony there. To this end, many countries carry out scientific research both on Earth and in space. The general purpose of these studies is to examine the effects of long journeys to and life on Mars on the human body, and how people who come here can sustain life. The National Aeronautics and Space Administration, NASA, conducted medical examinations of space mission astronauts in an attempt to clarify the effects of space missions on the human body systems. The space environment has three fundamental differences from the Earth environment. This zero gravity, low gravity, microgravity environments, cosmic rays, weak magnetic fields. Humans have lived in a gravitational environment all their lives, so all our organs and body fluids are located in body cavities and move accordingly. When you go to the space environment, this gravitational effect disappears. Additionally, the Moon and Mars are in a much lower gravitational environment than Earth. Earth's gravity is 9.807 meters per second squared. The Moon's gravity is 16% of Earth's, 1,622 meters per second squared, while Mars's gravity is 38%, about one-third, of Earth's, 3,711 meters per second squared. It is true that the effects of these environments on the human body are different than on Earth. As a problem other than microgravity, there is cosmic radiation, cosmic rays. In space, there is radiation emitted from two different sources. These radiation sources are the Sun and the interstellar galactic system. Particles of solar and galactic origin are usually low-energy protons, 90% or more, and electrons. Cosmic rays are very different from terrestrial radiation, both in terms of particle properties and energy levels. Therefore, the effects of cosmic radiation on the human body are different and are still being studied. After all, there is no Earth's magnetic field, geomagnetic field, in space, and astronauts live in a weak magnetic field. The absence of a magnetic field is another factor affecting the human body, as the magnetic field is an important tool in protecting the Earth from cosmic rays. Apart from all three of these variables, loneliness, altered day-night rhythms, and prolonged isolation and immobilization cause changes in human mental and cognitive function. The effects of the above factors on the central nervous system were studied using extensive brain scans of astronauts before launch and upon return from space. The results of all this scientific research also raise questions about the future of long-term space missions. This review first summarizes research on the effects of microgravity on the human brain, and then refers to the effects of radiation in space on the human body, especially the brain. For example, if you look at footage from the International Space Station, you can see that the faces of astronauts are puffier than those on Earth. In a zero-gravity environment, the fluid that would normally be distributed in the lower body is more evenly distributed over the whole body, and its upward movement causes this situation. That is, the body fluid cannot flow down. Lack of gravity affects the brain in many ways, just as it affects the whole body. In a study conducted by a NASA team, astronauts say the changes are affecting human functioning both physically and mentally. Because of this, astronauts have great difficulty controlling their movements and performing some conceptual tasks. An expert at the University of Texas Health Science Center, USA, tested his 3T magnetic resonance imaging, MRI, on 27 of his astronauts who had been in space for more than a month. A malformation was found in the astronaut's eyeball. In this study, MRIs of the brain and orbit were repeated on 8 astronauts who had flown into space multiple times. Optic nerve sheath thickness and optic nerve thickness were measured. 7 of his astronauts had flattened posterior eyeballs, 4 had optic nerve prominence, and 3 had hind limb depression and deviation in the pituitary curve. Similar to idiopathic intracranial hypertension, this is thought to be caused by increased cerebrospinal fluid pressure due to a microgravity environment with low gravity. However, this is not a controlled study and was not filmed prior to going into space. Therefore, it is unclear whether these findings occurred prior to launch. It has long been known that astronauts experience symptoms such as fatigue, nausea, headaches, and blurred vision during long space flights. However, the exact mechanism of their formation is unknown. Some authors attribute this to increased intracranial pressure. It has been suggested that cerebrospinal fluid, like other body fluids, moves upward during space missions in a zero-gravity environment, increasing intracranial pressure. In addition, it has been reported that performing a lumbar puncture on symptomatic astronauts returning from a space mission can reduce the burden on astronauts and improve their condition. Microgravity has been observed to cause unpredictable behavior not only in humans, but also in devices used to cool spacecraft components. During his experiments on the ISS in 2015, many researchers directly and indirectly observed that weightlessness drastically changes evaporation and condensation processes. This is an important discovery that will affect astronauts' physical function and change their nutritional and hydration needs during long space travel. In a 2016 statement by astronauts Scott Kelly and Mikhail Kornienko, astronauts suffered from microgravity-induced osteoporosis, muscle wasting, sensory impairment, nutritional deficits, and adjustment disorders during their long space journeys, said. To study these effects, NASA collected blood, saliva, and urine samples from the astronaut during his 340 days in space. These samples will be analyzed upon return to Earth, and the analysis results will be published later. Additionally, biological samples from astronaut Scott Kelly were compared and genetically analyzed with samples from his 340-day stay on Earth, identical twin Mark Kelly. As a result, Scott Kelly's telomeres were significantly shortened within the first 48 hours, but this shortening was later found to return to normal. But the most obvious change was a gene known as the cosmic gene. These genes play important roles in cellular processes that regulate hypoxia, mitochondrial stress, genetic processes, DNA damage repair, connective tissue processes, collagen, thrombosis, bone formation, and immune activity in the human body. Encodes a transcription protein. Astronaut Kelly's genes were 7% less normal than his twin brothers at the 6-month checkup. Microgravity, hypoxia, inflammation, and cosmic rays may be responsible for this genetic change. Simulating microgravity on Earth is extremely difficult. The parabolic flight, in which the plane ascends and descends at a constant angle, makes it possible to simulate a zero-gravity or microgravity environment, albeit for a short period of time. During parabolic flight, a person is free from her gravity for 22 seconds. This method is very useful for scientists working in the field of microgravity. Additionally, the method is much less costly and provides scientists with data on the type of habitat astronauts should have on the space station. Microgravity research is also done by sending satellites into space for short periods of time. To this end, China launched her first microgravity test satellite, SJ-10, on April 6, 2016, returning to Earth after a 12-day space journey. During its 12-day journey, the satellite performed 19 habitation experiments in microgravity. One such experiment was to study the development of mouse embryos under microgravity in order to elucidate human reproduction in space. Another experiment investigated the effects of radiation on the genetic stability of fly and rat cells. Previous studies on the brain have performed and compared MRIs of an astronaut's brain before and after a mission. In addition, several cognitive and cognitive functions were tested on astronauts who flew into space. So far, these studies have not been conducted in space because the International Space Station has not carried radiographic imaging equipment, although some studies using electroencephalography, EEG, have been conducted in space. I'm here. His 2/3 of ISS astronauts report blurry vision upon returning from space. Former astronaut John Phillips told the Washington Post that he boarded the space station in 2005 with 20/20ths vision and returned 6 months later with 21/100ths vision. His vision improved somewhat during his 6 months on Earth, but he was required to wear glasses. But Phillips said his experience in space wouldn't change for better eyesight, similar to the vision loss and intracranial pressure syndrome seen when astronauts return from long space missions. The symptoms have led researchers to this question. It is believed that microgravity causes fluid to move to the brain, increasing intracranial pressure. In addition, the upward flow of cerebrospinal fluid causes increased pressure in the optic nerve sheath, resulting in visual impairment. More than half of astronauts who have spent more than 6 months in space develop significant neuroocular symptoms. Astronauts lose their sight due to increased intracranial pressure, recognized by NASA as the greatest risk factor for long-term missions. Contrary to this idea, Lowry et al., an experimental study of 8 people showed that acute microgravity reduced central venous pressure and intracranial pressure. In this study, the aircraft created a zero-gravity environment with a 20-second rapid undulating cycle. That is, sudden microgravity was simulated in parabolic flight. In addition, researchers have shown that the pressure on the human brain from standing in zero gravity for more than 24 hours is slightly higher than that observed on Earth, but not at a pathological level. Increase. However, the study was not conducted in space, so it does not give a definitive idea of what the results would be for astronauts. In a study by Van Ombergen et al., a published study found that microgravity, containment, isolation, and immobilization were the factors most impacting astronauts during long space journeys. They found that long-term space travel, in particular, can have devastating effects on human physiology. To study the effects of microgravity on the brain fluids of astronauts, Alperin et al., they studied white matter hyperintense in brain MRI scans of 17 astronauts before and after the mission. Of these 17 astronauts, 10 spent long-term, 165 days on average, on the ISS, and 7 astronauts completed short-term, 14 days on average, space shuttle missions. A comparative MRI study found increased periventricular white matter hyperintensity in astronauts exposed to prolonged microgravity exposure. This increase is probably related to the increased volume of cerebrospinal fluid in the ventricles. However, no hyperintense changes were detected in deep white matter. This suggests that high white matter intensity is not responsible for the changes in cognitive performance that occur in astronauts after long-term space missions. Conducted a functional MRI study on a 44-year-old male astronaut who flew in space for 169 days in 2016, 30 days before flight and 9 days after returning to Earth. In this study, the authors detected changes in an astronaut's fMRI in regions related to the vestibular system and motor function. Neuroplasticity can be loosely defined as changes in neuronal function due to changes in future data inputs. It has been previously reported that neuroplasticity can also be impaired during long-term space missions. In a study they published, Koppelmans et al., pre- and post-mission MRI scans were performed on 27 astronauts who flew into space. After this study, the authors noted changes in the astronauts' gray matter. There was a decrease in gray matter, especially in the frontal and temporal lobes and periorbital area, and a slight increase in sensoromotor brain areas. These changes are directly proportional to the time spent in space. The authors attribute this gray matter change to a CSF shift, and changes in neuroplasticity. This is the most comprehensive MRI study ever done on an astronaut's brain. In particular, EEG is widely used in microgravity research. Because it is easy to carry, it can be taken out into space and recorded brain waves in space. Savora et al. In the study, he recorded the brain waves of 5 astronauts before, during, and after the flight. Alpha rhythms have been found to increase in the parieto-occipital and sensorimotor regions during spaceflight. Additionally, decreased alpha in the cerebellar and vestibular systems has been reported. This and similar studies suggested that changes in EEG waves may be related to emotional stressors. Roberts et al. Compared brain MRIs from 18 long-term, average 165 days, and 16 short-term, average 13 days, space missions in a published article. Showed that the constriction of the CSF region was more pronounced. They also showed that the ventricular system was enlarged in long-term workers. The authors suggest that all these effects led to elevated CSF pressures and visual disturbances experienced by the astronauts. So microgravity has a huge impact on both her CSF system and her gray matter. However, the impact of these effects on human cognitive function remains to be elucidated. Furthermore, in order to overcome this microgravity effect, methods of creating artificial gravity in space are being explored. One possibility is centrifugal motion. Rotation of a spacecraft in space can create a centrifugal effect and create artificial gravity. However, this is a very difficult system. Another risk in space travel is radiation exposure. This radiation is cosmic radiation caused by highly charged particles. As already mentioned, this radiation has 2 main sources. One is solar radiation, and the other is radiation from stars other than the sun, galactic radiation. The radiation dose an astronaut receives on his ISS during his 6 months is about 90 MSV. This is about 37 times the 2.4 MSV average dose he receives in a year from natural radiation worldwide. In addition, measurements made by the RAD instrument on board a dry Mars rover spacecraft show that the daily radiation dose that can be received on the surface of Mars is 0.7 MSV. The average natural radiation dose absorbed in 1 year worldwide is 2.4 MSV. This shows how high radiation levels are in space and on Mars. The effects of radiation on the human brain have been studied in patients who had previously undergone radiation therapy and in patients exposed to radiation accidents. But none of this is the kind of radiation that astronauts are exposed to in space. There is high-energy, fully ionizing nuclear radiation in the universe, which is mainly caused by galactic cosmic rays. The radiation produced by heavy charged particles in galactic cosmic rays causes severe and irreversible damage to cells, unlike the type of radiation on Earth. No technology has yet been developed to adequately protect the spacecraft hull and astronauts from these charged particles. NASA has been researching this for years, covering spacecraft with such radiation-resistant materials. Studies have shown that the hippocampus and frontal cortex regions of the brain are most susceptible to cosmic rays. Palihar et al. Studied the effects of intense ionizing radiation on mice. At the NASA Space Radiation Laboratory, mice were irradiated with He16O and 48 Ti, charged particle radiation at doses of 0.5 to 1.0 gray per minute, helium for 6 weeks. Cognitive tests, novel object recognition, object replacement, were performed in mice to demonstrate hippocampal and prefrontal cortex function and to examine mouse neurons in the prelimbic cortex. At the end of the study, it was found that radiation severely impairs cognitive function in the cortex and hippocampus and reduces synaptic integrity of neurons. Considering a trip to Mars also increases the importance of cosmic rays. Mars' atmospheric pressure is less than 1% of her pressure on Earth. As already mentioned, the gravity is about 38% of Earth's, which is what we call microgravity. Mars's atmosphere is composed of 95% carbon dioxide, 2.7% nitrogen, 1.6% argon, and trace amounts of carbon monoxide, oxygen, and water vapor. Moreover, the temperature on Mars varies from plus 20 degrees Celsius to minus 80 degrees Celsius, and even minus 150 degrees Celsius. Although the atmosphere of Mars is very thin, it can somewhat reduce the effects of cosmic rays, so the radiation dose is less than half of what a trip to Mars would receive. The maximum dose that can be absorbed during a trip from Earth to Mars and a stay of 500 days is 1,000 millisievert, or 1 sievert, which is believed to significantly increase cancer risk in humans. Attempts are first being made to create an Earth-like atmosphere on Mars to overcome the effects of these cosmic radiations. Enjoy watching. Do not forget to subscribe to the channel and press the like button for the continuation of such content.